We're beginning our study of thermodynamics by talking about temperature and thermal energy. And this will just be the first part. We'll have to split this up into two different lectures. I want to talk about temperature, maybe the definition of thermal energy, and then we're going to talk about some other things next time. But what makes things hot and what makes them cool? And I think the easiest way to understand this is to talk about a gas, but the same is true for liquids and solids, as you'll see. Suppose I have a container and it has a large number of molecules, and let's just say that it's air, and I have this container of air and I'm going to make it hot. Now if you look, I'm just going to draw a few representative dots that's going to represent the literally trillions of air molecules that are in this container. Okay, there's oxygen molecules, O2. Maybe this will be an O2 right here. And then there's a lot of nitrogen, N2, and a little bit of carbon dioxide, CO2. And these have different masses. If you have a particle, a CO2 molecule, it has more mass than an N2 or an O2. Okay, and in chemistry you can figure out what the mass is by counting how many protons and neutrons it has in the whole thing. Electrons are pretty much negligible. But anyway, each one of these guys is moving. Now if you look at a single molecule, so let's take a look at a single molecule outside here. Let's say, okay, it has mass and it's moving. So what kind of energy does it have? It has kinetic energy. Now, when we look at a large collection of molecules, see, it's very difficult to do physics on a single molecule. I mean, there are particle physicists that do it, but that's not what we're going to deal with in here. What we're going to do is we're going to look at billions, if not trillions, of these little particles, and we're going to average them together. And so what we're going to do is we're going to look at the average kinetic energy of all these particles, because some of them are moving fast, some a little bit slower than the others. Some have, a little bit of mass, some have more mass than others, but let's say that these things, and they bounce off each other and hit off the walls and stuff like that, but they're moving in all different directions, and that makes it a gas, and they're moving. Now let's suppose that if I were to actually take my finger and stick my finger in this gas, I go, ooh, that's hot. That gas is hot. Okay, but what if I had a container right next to it and the particles are moving, there's the same number of particles per unit volume, maybe it's just air, but these particles are not moving as fast. Now, if they're not moving as fast, what does that mean is true about their kinetic energy? Now, when I say they're not moving as fast, I mean on average. If I look at this individual one right here, maybe it's moving pretty fast. Maybe it's moving as fast as the average one of these. But because thermodynamics deals with molecules and atoms on a massive scale, on lots and lots and lots of them, we kind of look at averages. And so the way we feel, the way we detect what the average kinetic energy of these molecules are is we talk about temperature. So this would be hot, and these molecules we would feel them as being cold, because and cold stuff, the average kinetic energy of the stuff is much lower than stuff that's hot. Now, what do we mean by kinetic energy? That's how much work something can do. I mean, energy, these molecules contain more energy per molecule than these do. And so we have a name for how much energy something has because it's hot or cool. And that's called thermal energy. So thermal. It's the energy associated with the motion of the molecules. Now, by the way, it's kind of interesting if you have hydrogen gas that's at the same temperature. What is hydrogen made out of? What kind of molecules make up hydrogen gas? Well, it's not just hydrogen atoms. It's two hydrogen atoms glued together. It's H2. Well, let's take a look at an H2 molecule and an O2 molecule. Now, which one has more mass? The oxygen. Oxygen atoms are way bigger than hydrogen atoms, and so if I've got two of them, I got two of these, this is going to have a lot more, this has a lot more mass. It's just a lot bigger. Now, if they were at the same temperature, though, what's going to be true about the motion of these molecules compared to the motion of these molecules? Yeah. The hydrogen, in order to have the same temperature, is going to be moving on average a lot faster than these guys. Maybe not a lot faster, I don't know. There's a function. And if you take a branch of physics called Statistical Mechanics, which is really interesting, I've only had a little bit of it. It has to do with relative velocities of individual molecules and how you take an average of them or use statistics to figure out averages and so on. But the oxygen molecule, to be at the same temperature as the hydrogen molecule, will be moving a little bit slower because it has more mass. Because it's related to the kinetic energy. It's not exactly 1/2 mv squared, but it's very similar to that. And it has to do with the combination of mass and speed, how much kinetic energy, how much thermal energy the gas has. And by the way, this is one reason why, hydrogen is, if you get a hydrogen balloon, it'll rise because its molecules are moving faster because they're at the same temperature. So there's a lot to it, and we're actually not going to worry too much about that right now. But this contains more, if I have the same number of molecules in these two containers, because these guys are moving on average with more speed than these guys, this has more thermal energy. Okay. Now, what if I have a barrier like this across them? Let's talk about temperature. We have various ways of measuring this average kinetic energy, and we use a thermometer to do that. Now we have a Fahrenheit scale. Like, let's say what's a nice room temperature in Fahrenheit scale? Like right now, it's probably about, I can see the thing, it's 71. It's 71 degrees Fahrenheit. Now, the way you get that is you stick there's a thermometer in there, and it compares the average kinetic energy of the air molecules to some scale. The Fahrenheit scale is a very nice scale, actually, to use when it comes to talking about the weather. 0 degrees Fahrenheit is like a cold winter's night up in the mountains or in the East Coast. Okay, a really hot day here in Clovis is 100 degrees. So it really has a night from 0 to 100 degrees Fahrenheit. It gives you a nice scale for talking about the weather. So, like most standard units, like miles and inches, I don't like them. I think the United States should go to inches. To centimeters and meters and kilometers, because those units make a lot of sense and they're much easier to use once you get used to them. But the Fahrenheit scale, it's a nice scale to use when you're talking about the weather. So if we keep the Fahrenheit scale, that's okay with me. But scientists don't really like to use the Fahrenheit scale. We like to use two different scales that are very closely related that you probably remember from chemistry, right? We have the, if it's 71 degrees Fahrenheit, that's about a nice cool, it's fairly cool in the room. A cool room temperature would be 20 degrees Celsius. I'm not sure if this is exactly the right conversion. We could figure it out, but 20 degrees Fahrenheit, degrees Celsius, that's a nice, cool room temperature. And now the Celsius scale is based on water, and that's why scientists like it. If you have 0 degrees Celsius, that's the temperature at which ice will melt. Or that water will start to freeze. Same kind of process. 100 degrees Celsius is when water boils. So if you're dealing with chemistry where you're going to be freezing stuff or you're going to be boiling stuff, this is a very nice scale to use. 0 to 100 goes from the melting of ice to the boiling of water. So it's a very nice scale to use. Now, using this scale, basically what they did was they took a thermometer and they measured ice melting and they put a little scratch in it and they said, we'll call that 0. And then they boiled water and put the thermometer in the boiling water and saw where the mercury went, and they put a little scratch in it and they said, we're going to call that 100 degrees Celsius. And then we just divided the difference into 100 little scratches. And each one of those increments was a degree Celsius. But then somebody said, well, look, if temperature is a measure of how much motion these molecules have, what their average kinetic energy is, what would be the temperature in degrees Celsius if the molecules stopped moving altogether? Anybody remember from chemistry? At what temperature will the molecules stop moving? It's a little bit under 273, but 273 is close enough. At negative 273 degrees Celsius, these molecules will stop moving altogether. Now that's, by the way, impossible. You cannot make something so cold that its molecules will completely stop moving. That's a law of quantum mechanics. So if you go on and study more physics, study quantum mechanics. It's very interesting stuff. Okay. Well, scientists were a little bit unsatisfied with this, so they created a new scale. It's based on the Celsius scale. It's incremented the same, but they said, let's start at the coldest impossible temperature. What temperature, when the molecules stop moving, we'll call that 0 kelvins. Therefore, when ice melts, instead of melting at 0 degrees Celsius, ice will melt at 273 kelvins. And water will boil 100 degrees later at 373 kelvins. And then, okay, nice, comfortable room temperature, about 293 kelvins. Okay, so that's the temperature scale that we're going to use. And the homework is basically on the first part of the homework that I want you to do. Practice problems 1 through 4. Which is what I want you to do for homework, is basically converting from kelvins to degrees Celsius and from degrees Celsius to kelvins. If you get that done, that's a good start.